Yeah, so today I'll be giving an introduction on Bactopia for bacterial genome analysis. To start off, I think it's probably important that what is Bactopia? So let's go ahead and introduce it and kind of highlight its impact so far. Bactopia is an end-to-end pipeline for the uh, analysis of bacterial genomes. It's written in Nextflow. It follows NF-core standards. It's available from Conda, Docker, or Singularity, and it supports numerous compute infrastructures. If you've used Nextflow, anything that Nextflow supports to be executed on, that could be your laptop, desktop, servers, HPC systems, the cloud systems. Bactopia also supports it. It wraps more than 150 bioinformatic tools into standalone modules, which are kind of cool because you can kind of shuffle those around like Lego pieces. And it has an active user base that's providing regular feedback. This includes the folks here at Wyoming. We use it on a regular basis and we are always adapting it to our needs, but as well as global users from academia, government, and commercial entities. And surprisingly, which is uncommon in bioinformatic tools, we've been able to maintain it for over 5 years now. Unfortunately, many bioinformatic tools are graduate student projects. This was a graduate student project, being me. And typically what happens is graduates graduate and they need a job, and not all jobs allow them to maintain the tools that they've built. So I've been quite fortunate to be able to consistently maintain Bactopia through support from my admin. Bactopia so far, which is kind of cool. I'm just one guy in Wyoming. It's been cited over 150 times, so it's nice to see that it's being able to enable, or it's able to enable other people to do their research. Over on the GitHub side, there's 467 stars, which to me is pretty cool because that means somebody took the time to say, "Hey, I like this." But it's been used in all sorts of bacterial genomic studies. The website has had over 50,000 unique visitors. In the past, that was kind of cool, but now I'm like, are these just AI crawlers just trying to slurp up everything? But many of these users are around the world. There is a pretty high uptime on the docs, which is cool. That means people are actually reading them. And it's been downloaded over a million times. And for those that don't know much about Wyoming, I'll confess I didn't know much about Wyoming before I moved out here. But 1 million downloads is about almost twice our population here in Wyoming. And Wyoming's probably bigger than Georgia and South Carolina put together. So a lot of land, very few people. To give you kind of idea around the world where Bactopia is being used, these are all the locations that I could kind of piece together from personal communications. But these are people from public health labs like myself, researchers, students, sequencers, and from the industry. But it's kind of cool that we've got almost everywhere covered, or the major continents covered these last 5 years. Before I get into Bactopia, I just want to introduce some of the people behind Bactopia so you can kind of get an idea of what's happening in the background. Yo, y'all already know I'm Robert, but I'm Wyoming's bioinformatician and the developer of Bactopia. Tim Reed, who I worked with for quite some time at Emory University, and I still work with Tim. We meet regularly. He's kind of like I would say, make sure Robert's on the right course during the graduate school. But Tim is basically helped kind of guide Bactopia for a while and shape the ideas that we put into Bactopia. Dr. Joe Reed here at Wyoming, he's our lab administrator. He's given me his full support to continue to develop Bactopia and use it to strengthen our genomic surveillance here. Jim Mildenberger, our molecular lab supervisor, he's always given me good ideas and he's helped introduce new features, more so on, hey man, can this do that? And it's like, right now, no, but yes, we can do that. So ONT support came from suggestion from Jim. Taylor Fearon is our NGS supervisor. Taylor's great because she's constantly using Bactopia and constantly giving me feedback, and she's been pretty critical in helping expand Bactopia's usage out of academia over at Emory and into public health. And then the many Bactopia users, like I said, these come from all sorts of people across the world, but they're always giving me feedback for new features, improvements, and always finding bugs to fix because there's always some bug to squash. So what is this Bactopia pipeline? Let's go ahead and take a look at it. But before we do that, there's an unwritten rule and when you're developing next flow pipelines that you got to make a metro map to kind of to highlight what your pipeline does and a flow chart of your pipeline. So yeah, every pipeline needs a metro map. And unfortunately, here in the US, we don't have too many metros. They're essentially unicorns. So what I give instead is a roadmap. So here's kind of the basic outline of Bactopia. It includes routine yet essential steps in bacterial genome analysis. We have gather, QC, assembly, annotation, sketch, antimicrobial resistance, and MLST. But from the start, Bactopia is flexible. It supports short reads, long reads, and assembled genomes. So if you, depending on what your input is, Bactopia likely supports it. And those reads, which I'll talk about here. Oh, this is fun. So I put these together on a Windows machine, and now I'm presenting on a Mac machine, and the standard, like, it's slightly off on Mac. So bear with me. But yeah, so short reads and long reads are supported. These reads can be from the Sequence Read Archive or the European Nucleotide Archive, or you can provide assembled genomes because there are some samples where we don't have the raw reads, we only have assemblies. And those assemblies can be user provided or pulled from NCBI. And so when you do this, the sequences are automatically assessed and cleaned to ensure reliable downstream analysis. This includes trimming, filtering, and quality checks. So basically, we want to ensure that the data is good going downstream. So kind of at these gather and QC steps, we make sure that is your data good enough to complete the pipeline? Otherwise, we'll stop there because there's no point in wasting a bunch of time for some samples that are going to fail. You as a user can adjust those parameters. For example, if you know it should work, you can lower the thresholds to make it work. Yeah, so Bactopia also adapts by utilizing multiple assembly strategies out of the box. Like I said, we can support short read, long read, hybrid, and short read polish assemblies are supported. So yeah, the hybrid would be you assemble with the Illumina first and then try to bridge the contigs with the long reads. And the short read polish would be the opposite, where you assemble with the long reads first and try to polish the assemblies, correct the errors of ONT with the Illumina reads. And then the final steps, they deliver annotations, AMR predictions, and MLST type-in and genome sketches. So kind of these steps give you kind of everything you want out of a bacterial genome. This will take 5 to 20 minutes, depending on how much did you sequence. So obviously a 50x coverage sample is going to take less time than a 200x coverage. But during that QC step, we will reduce to a maximum of 100x coverage because we've kind of found that after 100x, it's kind of diminishing returns. You're spending more time to get very similar results. And then even some tools, they actually perform worse when they have too much coverage. Basically, they can't differentiate a random error from a true error. You start these random errors accumulate with so much coverage. Yeah, and like I said, depending on what resources you have available, it's obviously going to take longer to run on your laptop than the HPC system. But when it runs all these steps, it puts all your output files into a standardized directory structure. And this is quite useful for what happens next. But in these outputs, you get an extensive audit trail. So anything that you might be interested, logs, staging information, versions, all that fun stuff, you have all that available to you. Oftentimes, that's something we look at when there's an issue. But no matter what, they're always there for future uses. And when possible, the outputs will automatically be merged. So this could be like all the QC summaries. We can merge that into a single file. All the they stay as individual files, but we do have a secondary merge file that you can look at. And then assembly stats, that sort of stuff, MLST outputs, they can all be merged into single files, so that way you don't have to do it. But what else does Bactopia do? And in order to do that, we have to take a look at what I call Bactopia tools. At its core, these core steps of Bactopia, they structure all your data for smooth integration into downstream workflows. So like this is just like the first pass. Give me everything I need to do everything I want to do. So this is where the fun starts to happen. If you after you run Bactopia, now with a simple parameter change, you can run what's called these Bactopia tools. And so, for example, here, this red line, it'll use the process FASTQ files to run tools that have FASTQ files as inputs. And that could be stuff like Ariba, Bracken, Kraken, Midas, Sylph, mini tools. Oftentimes, they may just be one-off. So Ariba would be a simple tool. It just runs Ariba. But they could also be quite complex. They could be for things for calling SNP-based biology or creating SNP-based phylogenies or dehosting reads. So for example, here with a simple parameter change, you can run SNPy and it'll go and download any assemblies that you might want to include or any reference sequences that you might want to include. Run SNPy core, remove recombination events, then run IQ tree to produce a tree and produce a heat map SNP-Dis using SNP-Dis. But essentially, all you have to do is change one input, and Bactopia will know, hey, I need to go look for this FASTQ file, run SNPy, and do all this fun stuff. So to me, it's where I wanted to create something simple that I just change one parameter and I can run another tool, change one parameter, I can run another tool. Because oftentimes we may be in the lab, we may just want to do a quick like test, and this allows us to do that. And similarly, you can, all these pieces could be picked up and rearranged in the pipeline. It's basically kind of like the old little preschool toy or little kid's toy where the triangle goes in the triangle slot, the circle goes in the circle slot. But then you will have somebody that will try and put the square in the circle slot. But, you know, sometimes it works, sometimes it doesn't. But it doesn't stop there. As with the QC FASTQs, assembled genomes can also be processed with a wide range of Bactopia tools. This includes all your fun things like Abricate, AMR, Bacta, Busco, all the checkms, GZDB, TK, Mob Suite, Plasmid Finder. But essentially, these are all a single parameter change. Real simple, and I'll give you an example of how that works here shortly. Oh, bummer. But then, yeah, you also have a bunch of species-specific tools that you can run. And unfortunately, Mac decided to display it differently. But yeah, so you can basically you can run each individual species-specific tool with the parameter change, or I created a tool called Merlin, which does have one of those acronyms that there's an acronym for it. I think it's like Minmer assisted something something something. But where basically it'll say, it'll take your assembly and then do a quick match distance against representative samples for each of these tools. And then, for example, if you sequence E. coli, Merlin would query your sequence against our match sketches and say, hey, this is E. coli. Now I'll proceed to run the E. coli tools. If you really wanted to, you could force Merlin to run every tool, but there are some tools that they fail with exit codes that aren't proper when they get a negative result. So basically, if you a good example would be pneumocat. If you don't give it a strep pneumo, it will fail spectacularly. And instead of just saying this isn't strep pneumo, it will cause everything to crash. So that's one tool where it's not included in the it can run all type thing. But yeah, essentially this is a bunch more tools that either take the QSeed FastQs or the assembled genomes and allow you to rapidly just run those. And those can be grouped together. A good example here is Staph Typer. So my graduate work came from a staph lab, Staph aureus. So we have Staph Typer, which will run 3 additional tools to type staph. But instead of running like Aggravate or SCC-MET, you can run Staph Typer and it'll run all these tools. And then even after the annotation step, there's even more tools that you can make use of. The annotations can be queried against any samples or any sequences that you want using BLAST. There's AMR Finder, which is included in the main pipeline, but there are custom AMR Finder databases that you may want to run, and things like Eggnog and 5SPY. But you can also do complex workflows. This is really bumming me out with the Mac bit, but I'll share these slides with everybody so that y'all can take a look at them. One is this: there's a pipeline for pangenome analysis. You can either run Panaroo, Pirate, or Rory, depending on which tool you want to use to create the pangenome. Currently, the default in Bactopia is Panaroo. Originally, it was Rory because at that time there was only Rory. Then it was Pirate because at that time there was only Rory and Pirate. And now Panaroo, which is a bit better than the other two, but they all serve their different purposes. So it's up to you as a user to determine which one you want to use. But typically Panaroo does the best. And then similar to the SNPy pipeline earlier, there is a clonal frame ML that will allow you to remove recombination from the pangenome. And then you could create a phylogenetic tree, create a heat map from the synthesis, or you can do some GWAS with Scori. But again, that's just a simple parameter change. You would just type pangenome. There is an option to include publicly available assemblies into your pangenome analysis. So for some organisms, that's quite nice. There's not too many samples. So something like Salmonella enterica, where there's 600,000 plus samples, that wouldn't be a good idea. But if you are sequencing something that's kind of rare and there's 50 other available samples, you can just include those into your pangenome to kind of get an idea of where your sample lies. Yeah, so here's kind of an example. And those images I showed, there's more than 65 of these additional workflows, Bactopia tools, that allow you to really quickly do more science. They take advantage of that output structure that the original core Bactopia pipeline creates. And that sample structure or that directory structure is built per sample. So the basic unit is the sample, it's not the run. So that way, this allows you to continuously add samples over time instead of having to add runs together, which is a bit more tedious, whereas now the samples can be moved around as needed. but they're just a simple workflow or a simple parameter change, that dash dash workflow WF. But like I said, these include many categories: organism specific, mobile elements, AMR, pangenome, SNP and DELS, taxon, phylogeny. But here's an example of what you could do. To process Staph aureus samples, so Bactopia dash dash samples, you can provide a sample sheet, or there's ways to just process a single sample at a time. So imagine this sample sheet had a couple hundred samples in it. You could run them through Bactopia, and then from there to run the Staph specific tools, you could just Bactopia dash dash workflow Staph typer, and Bactopia will know to go find your process samples, and then based on what it finds, you can run these Staph typer tools. And then similarly, you could run the SNP workflow, provide an accession. Bactopia will go and download that accession for you, and then run SNP and call SNPs for all your samples against that reference genome, and then build a core genome or a core SNP tree. But again, it's really the key is just changing these parameters and adjusting. No need to go figure out how to run SNP, or how to run each of the Staph tools, the AGR, SCCMEC, or SPA tools. The idea is those are all built in for you. Bactopia also supports the All the Bacteria project. And if y'all haven't heard of that project, I encourage you to go take a look at it. It's from Sam and Iqbal's group over in the UK. He was at EBI. And basically what they did was they said, hey, we have all these bacterial genomes. We have access to some fun resources. Can we just assemble them all? And so they ran over 2.5 million bacterial genomes through Shovel, and now you have access to 2.5 million, and it's more than that now, assemblies. And so to me, it's quite nice to say, hey, we have all these assemblies. Can I just integrate them into Bactopia? And so what we did is we created two functions, Bactopia ATB downloader. And what this will do is it'll go and download all the bacteria assemblies. And you could do this by biosample, tax ID, or species. So the All the Bacteria project, they use biosample as their sample ID. And so if you have a list of sample or publicly available samples that you want to include, you could, or a good example is there's a paper and you wanted to include those samples, that sort of thing. But what this does, it allows you to rapidly download all their assemblies, and they've done an amazing job compressing all their assemblies. So you might think 2.5 million assemblies would take up a lot of space, but the way they've compressed them, it's like, I wouldn't say it's uncompressed, it's terabytes, but it's maybe 100 gigs, which is not that bad at all. But yeah, after you download the samples, there is another tool that is not another downloader, but a formatter. It's ATB formatter, and it can arrange all your ATB assemblies for Bactopia tool usage. So basically what it does is it mimics the output structure of Bactopia so that you can rapidly process these samples. It is limited to only the tools that support assembly inputs, so FASTA inputs. Obviously, you can't run something that requires a FASTQ file if you don't have the FASTQ file available. To give you kind of an example of how this works, you can download Staph aureus samples with just Bactopia ATB downloader and query 1280. 1280 is the tax ID for Staph aureus, so you could either give 1280 or you could just type out Staph aureus. And then after that, you would just, after that download finishes, you would then format the output, so that basically format the output directory structure so that it could then be used to run Bactopia tools. So this may take a while. This takes seconds. It doesn't take very long. But then you have access to all those tools that use fast inputs. So you could do the simple Bactopia -test workflow, SSEMech or Mob Suite for if you were interested in plasmids, or if you wanted to build a tree. I would recommend building a pangenome if you just download 100,000 plus assemblies. So the nice thing about the Bactopia tools is there is an option to include and exclude samples. So you could provide a list of samples that you want to include. So for example, you could say, in step 4-ish, you could say, here's a sample that we got in the lab. We could run a Bactopia or run a tool, Fast ANI. There's a Bactopia tool for that, but Fast ANI would calculate the average nucleotide identity amongst all the samples. And then you could say, I want all the samples that are within a certain distance from my sample that I'm interested in, and then build a tree based on that, just so you can get an idea of how your sample compares to other samples. So there are ways to kind of reduce the amount of data and kind of zero in on what you're interested in with these Bactopia tools. One example that we used was we were interested in like the bacillus, a particular species, and we did the whole genus and then zoomed in on the species we were interested in. To give you an idea of how simple this is, when I wanted to run Defense Finder, which searches for phage defense systems in samples, I ran it on, this is Salmonella enterica. So I did those Bactopia downloader and formatter, and then -- Defense Finder. And it's like one of these, like this is a screenshot, it was incredibly boring. But we processed almost 650,000 samples. And this is used in a cluster we have here in Wyoming. But 6 days and not much happens other than we process 650,000 samples. So it's like a good board, as in like there's not a bunch of red text telling you stuff's broken, it's not working. But it's one of those where it almost feels unreal for it to be so simple to run so many genomes through a pipeline. And this is complements the Nextflow for building a nice queue system within Nextflow. So yeah, like 6 days go by and we have Defense Finder results for 650,000 genomes that other people can now use. But yeah, let's go ahead and wrap this up, and we'll talk about what's next and all that fun stuff. Yeah, so if you are dealing with Nextflow any, Nextflow is making a lot of changes in their language. And unfortunately, on the Bactopia side, I was a huge abuser of their language. If there was something I could bend or adapt to my needs, I did. And a lot of that is going away in future Nextflow versions. So if any of y'all develop Nextflow stuff, I'd be happy to answer any questions related to that. But yeah, so I'm rewriting Bactopia for version 4 right now. It's close, and I hope to start having people test it out maybe next week. So if you're interested, let me know. But basically, I'm rewriting so it's compatible with future Nextflow versions, and these compatibility changes are probably for the better. I'm also going to be adding long overdue visual reports. I think that's one of the missing things that Bactopia's lacked for a while, is the ability to just say, okay, cool, you give me all these output files, but I need a summary that I can hand to somebody else and they can just quickly assess what they need to take from it. And then based on user feedback, more features and more quality of life improvements, simplifying some things that maybe are a few extra steps. But if you're interested, and again, I'll share these slides, but there's an issue on the Bactopia GitHub that has the full list of all the things that are going to be coming with version 4. I also plan to revamp all the docs, more tutorials, on getting started on particular systems. There's a tutorial in there to, process genomes, but it's not very helpful if you got to get up on AWS or if you got to get your cluster figured out. And the nice thing is with Nextflow is if you figure it out for Bactopia, it works for every other Nextflow pipeline. If you figure it out for another Nextflow pipeline, it works for Bactopia. So it's not a you set it up and it only works for Bactopia type situation. It's awesome because it works for every Nextflow pipeline. But yeah, more expanded tutorials. The current tutorial is just a basic let's process some genomes and nothing else. But I'd like to expand some of these tutorials out to utilizing those Bactopia tools for let's reproduce what a publication has done using their samples and building a pangenome tree, that sort of stuff. And then materials for workshops for if people are interested in running their own little workshop or whatnot. But yeah, to sum it all up, Bactopia is an extensive pipeline that allows its users to focus more on the science behind their samples. Thankfully, it'll continue to be sustained for another 5+ years through support from Wyoming Public Health Laboratory, Emory, CAPE, the Center for Applied Pathogen Epidemiology, and CZI's Open Science program. And yeah, there are many folks around the world using Bactopia. I still think there's still a lot of stuff that we plan to include in Bactopia, and there's still only scratching that surface. I'd quickly like to acknowledge the many developers of open source software. Bactopia uses a bunch of open source software tools. When possible, I try to help keep things rolling with those tools. So if I find a bug in one of those tools, I will try to submit a pull request upstream to that tool. On the Bioconda side, if there is an issue with the recipe, I'll work to get it fixed. And then, yeah, the many users who are helping to evolve Bactopia. Folks at WPHL, Taylor, Elena, Marin, Chase, Jim, Rob, and Joe. And then over at Emory, Tim and the Emergent Group, and Babaker over in Rush University in Chicago. But yeah, one final message, which doesn't come quite as nicely on this Mac. But yeah, I think by the end of this, I think it's better to think of Bactopia as more than just a pipeline, but instead an entire ecosystem of tools that we've been able to utilize based on this core pipeline. And this will continue to expand over time. With that, I'm happy to take any questions. And if you want to learn about Bactopia, feel free to check out the docs. Or if you want to contact me, there's my email over at Wyoming.